Okay. So just give me a thumbs up or something if you can hear me. I can see Ross and William. Cool. Okay. So again, unmute yourself if you have a question during this, and then I will address it. Or if you want to type it in the chat, that's fine as well. I'm gonna try and make this a shorter class than the last time, so let's get going. All right. So the new problem we have right now is if I were to pose to you guys that I wanted you to evaluate the sine of 15 degrees, the problem you would run into right now is that if I didn't let you use a calculator to approximate, 15 degrees is not one of the special angles that we've studied so far from our unit circle. That doesn't mean it doesn't exist though. So right now we'd be stuck right away because we don't know how to evaluate the sine of a 15 degree angle. We do, however, know that a 15-degree angle can be constructed from two of our special angles. For instance, 15 degrees could just be something as simple as 45 degrees minus 30 degrees. Or we also know that 15 degrees could be constructed using a 60-degree angle and a 45-degree angle if we subtract. Or we could use 135 and 120 degrees and subtract. So we can construct a 15-degree angle using two of our special angles. And with that in mind, it would be nice if we knew something like the sine of 15 degrees equals the sine of 45 degrees minus 30 degrees. So I know so far that's definitely true because 45 minus 30 is 15. And again, it would be nice if we were able to say something like that's equivalent to the sine of 45 degrees minus the sine of 30 degrees. That would be nice. However, that's not true. Okay, so this does not work. However, we can come up with a formula that does work. And if we were in our typical class session, what I normally do is derive the formula that does work together. But because of our unique situation, I'm just going to give us the formulas. Okay, so this doesn't work just subtracting two different signs because it's not like I can distribute a sign inside to both as if it was multiplication. Okay, so what we need though instead are these formulas, and they're called the sum and difference formulas. So there's a sine difference formula and a sine sum formula, and there's a cosine difference formula and a cosine sum formula. So here, capital A and B are just representing two different angle measures. So if I have the sine of angle A minus B, what the formula tells us is that that's equivalent to the sine of the first angle times the cosine of the second angle, minus the cosine of the first angle times the sine of the second angle, which is similar if I had the sum, but instead I have addition in the middle. For cosine formulas, instead of sine and cosines being multiplied and then added or subtracted, notice that we have two cosines and two sines being multiplied, and then we have the opposite operation in the middle. So for the cosine difference formula, we're actually adding the product of the two cosines and sines. And for the cosine sum formula, we're actually subtracting the product of the cosines and the sines. Whereas for the sine formulas, we're multiplying the different operations. So sine and cosine get multiplied together. And in the middle, we have the same sine, SIGN sign for the operator. So the difference formula uses subtraction and the sum formula uses addition. So again, if we were in our regular class setting, I would have actually derived the sine difference formula so you can see where it comes from. But because of our situation, I'm kind of just spoon feeding you these formulas right now. So if this were, if you were studying for a quiz or something, these would be the things that you put on a flashcard to study. Okay, there are tangent sum and difference formulas, but I never had to learn them when I was in high school, even as a math major. So I only realized there were actual formulas for them when I became a teacher and looked it up. So because we already know that tangent is just sine over cosine, y over x, we don't really need to memorize the formulas for tangent because if we wanted the tangent difference formula or the tangent sum formula, we could always just use the sine over cosine. Okay, so these are the formulas that are going to be really important for today's class and then for the homework that's going to be due on Monday that I'll talk about in a little bit. So now that we have this sign difference formula, we can actually go ahead and evaluate the problem that we weren't able to evaluate on the previous page. So now using that formula, I know that the sine of 15 degrees
Why would he ever make us? Why does it have to be collected?
So we can hear some of you. If you don't mute your mic, we can hear what you're talking about. So sine of 15 degrees equals the sine of 45 degrees minus 30 degrees, as we said before. And now that I have my sine difference formula, I can actually go ahead and solve this. So the sine difference formula, which I put above, says that I take the sine of the first angle, which in this case is 45 degrees, times the cosine of the second angle, which in this case is 30 degrees, minus the cosine of the first angle times the sine of the second angle. And then now we have four terms that we can evaluate because we know what the sine and cosine of 30 and 45 degrees is. So sine of 45 is our root 2 over 2, times cosine of 30 degrees is our root 3 over 2, minus cosine of 45 is root 2 over 2, and sine of 30 degrees is 1/2. So after evaluating those, now we're just multiplying and subtracting. Root 2 over 2 times root 3 over 2 gives me root 6 over 2, root 6 over 4, minus root 2 over 2 times 1/2 gives me root 2 over 4. And we have a common denominator here, which means I can add these things together. So that leaves me with root 6 minus root 2 all over 4. And radicals, although we can multiply them and divide them together, we can't add or subtract them unless they're the same kind of radical. So root 6 minus root 2 is not, for instance, root 4. That's not correct. So these are unlike terms, which means this is my final simplified answer. Questions to this point? So again, all I'm doing is plugging into a formula, which doesn't require too much thought. As long as you know the formula, you can plug in, and as long as you know your unit circle information, then you should be fine with getting your answer. So this was an example using degrees. I want to do an example using radians. So let's say we had to evaluate the sine of 5 pi over 12. Now, I've seen students before convert 5 pi over 12 into degrees so they could figure out two angle measures in degrees that add or subtract to give this radian measure. But the other thing you can do is simply on the side, I say to myself that 5 pi over 12, I need to generate a 5 pi over 12 angle using two other pi over 12 angles. I'm going to find one where I can subtract them. So now I just need to figure out the numerator multiplier of pi, and I want two of them that subtract to give a 5. I also want them to reduce with the 12 because I don't have special angles that are pi over 12s, but we have pi over 3s, pi over 4s, pi over 6s, pi over 2s. So for instance, if I wanted to pick something like 6 pi over 12 minus 1 pi over 12, I know that that's 5 pi over 12. 6 pi over 12 reduces to pi over 2, but the problem is that 1 pi over 12 doesn't reduce, and that's not one of my special angles, so I would be stuck. So the combination of subtracting 6 and 1 pi over 12 to get my 5 pi over 12 is going to fail me. So instead of 6 and 1, maybe I would do something like 9 pi over 12 minus 4 pi over 12. Because both of those angles now reduce, 9 pi over 12, if I divide top and bottom by 3, becomes 3 pi over 4, which is one of our special angles. And 4 pi over 12, when we reduce, can be divided out on top and bottom by 4 to get us pi over 3. and that also is one of our special angles. We also could have used a combination of 8 pi over 12 minus 3 pi over 12. Both of those subtract to give 5 pi over 12, and both of those angles reduce as well to give us special angles. So there are lots of combinations of things you can try, okay? Am I still presenting? Are we still good? Okay, thanks. So I'm going to use this combination. So now I have that the sine of our 5 pi over 12 angle is equivalent to the sine of 3 pi over 4 minus pi over 3, as my side work indicated. And then now again, I'm just going to use my sine difference formula, which I have up top again. So this says the sine of the first angle times the cosine of the second angle. Sorry, my computer's lagging a little bit. Minus the cosine of the first angle times the sine of the second angle. And now we'll evaluate these. Sine of 3 pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. Cosine of 3 pi over 4 is a negative root 2 over 2, since we're in quadrant 2, where cosine is negative. And sine of pi over 3 is root 3 over 2. Now multiplying gives us root 2 over 4 for the front terms. On the back, we have a negative root 6 over 4, but because I'm subtracting, we have a double negative, which will give me a positive root 6 over 4. And again, these have the same denominator, so we can combine them, and root 2 and root 6 are not like terms, so those can't be fused together. So my final answer will just stay root 2 plus root 6 all over 4. Questions there? Same process, just in the first part of the process, I just needed to figure out two angles that are special angles in radians that would subtract to give me what I want. Again, if it's easier for you guys to convert 5 pi over 12 into degrees, because we know our conversion formula of multiplying by 180 over pi, you could convert first, get a regular number that you're used to seeing, and then figure out, how to subtract degrees to get the number. But as long as you're using radians in terms of, in this case, pi over 12, just find two angles that add or subtract that would reduce, because that would give you the angle you want. Okay, so I just want to do one more of these, this time using a tangent though. So evaluating tangent of 15 degrees, we already did the sine of 15 degrees, but I want to walk us through if we had started this kind of problem from scratch. Then again, we know that tangent by definition is just sine over cosine. And we know that 15 degrees, like on an earlier page, was just 45 minus 30. So first I'm going to represent 15 degrees is 45 minus 30. Now I'm going to show that the tangent of that is simply the sine of that divided by the cosine of that, because that's our quotient identity. Tangent is sine over cosine. And then now I would expand both the numerator and the denominator using my formulas. So in the numerator, I would use the sine difference formula, and in the denominator, I use my cosine difference formula. So we already did the numerator because that was our first problem, but let's assume we didn't. So that numerator would be sine of 45 degrees times cosine of 30 degrees minus cosine of 45 times sine of 30. So same thing we did before, all divided by. Now my denominator, I need to use the cosine difference formula, which says multiply the two cosines together and add the product of the two sines. So here I have cosine of 45, cosine of 30, plus sine of 45, times sine of 30. Now, a common mistake that students make every year is canceling illegally. So for instance, people see, oh, well, cosine of 30 and cosine of 30 can just cancel each other, for instance. Or sine of 30 and sine of 30 can cancel. But this canceling is illegal because of the subtraction and the addition between the two things. If everything was just being multiplied and divided, then it would be okay to cancel. But because we have addition and subtraction involved, that canceling is illegal. So we can't do that. So instead, at this point, we're just going to evaluate each of these things using our unit circle. Sine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. Minus cosine of 45 is root 2 over 2. Sine of 30 is root 3 over 2, 1/2. So that's the numerator evaluated out. Denominator, cosine 45 degrees is root 2 over 2. Cosine 30 degrees is root 3 over 2. Plus, sine of 45 degrees is root 2 over 2. And sine of 30 degrees is 1/2. Now again, it's still illegal to cancel because of that subtraction and addition, so nothing has changed there about that. So I'm going to keep simplifying. Root 2 over 2 times root 3 over 2 is root 6 over 4. Minus root 2 over 2 times 1/2 is root 2 over 4. All of that being divided by the same products here, so root 6 over 4 plus root 2 over 4. It's still illegal to cancel because we still have subtraction and addition. I'm going to fuse these terms together. I'm going to bring this work up here. So combining the fractions, we now have root 6 minus root 2 over 4 in our numerator. And we have dividing by root 6 plus root 2 in our denominator over 4. Now we have fractions with the same denominator and we're dividing, so we could keep change flip and cancel the 4's, or we could just use our shortcut and realize that when we're dividing fractions with the same denominator, they cancel each other. So this now leaves me with root 6 minus root 2 divided by root 6 plus root 2. Again, still illegal to cancel because we have subtraction and addition. They're unlike terms, so I can't fuse them together. This is not yet done. Does anyone know what the next step would be that we've talked about before?
Can't you not have radicals in the denominator?
Right, so we don't want to have radicals in the denominator, so what process would we use?
You would multiply by the radicals?
Yeah, which radicals in particular?
The denominator.
Yeah, so what am I going to multiply top and bottom by?
Root 6 plus root 2.
Root 6 plus root 2?
Root 6
No, root 6 minus root 2.
Root 6 minus root 2, right. We're going to multiply by the conjugate. If you go back to Unit 2 when we simplified dividing radical terms. So I'm going to rationalize the denominator by multiplying top and bottom by the conjugate of the denominator. So now up top, if I FOIL, root 6 times root 6 would give me 6, or if you prefer, that's root 36, which then you can make a 6. Root 6 times negative root 2 is going to give me negative root 12. Remember, although I can't add or subtract radicals together underneath, I can multiply underneath or divide underneath when you're using radicals. The negative root 2 times the positive root 6 is going to give us another negative root 12. And the last term's negative root 2 times negative root 2 is going to give me a positive 2. Or if you prefer, a positive root 4, but square root 4 is just 2. So that numerator now is FOILed out. In the denominator, the whole point of using a conjugate is that we will cancel the middle terms, but I'm going to show everything just in case I lose anyone. Root 6 times root 6 is 6 again. Root 6 times negative root 2 is negative root 12. Positive root 2 times positive root 6 is a positive root 12, and now you can see why the conjugate canceled the middle terms. And then positive root 2 times negative root 2 is a negative 2. Now I'll just combine like terms. So in my numerator, 6 plus the 2 on the end gives me an 8. Negative root 12 minus root 12. Here we're subtracting and they're both the same kind of radical. So that's just like me having negative x minus x, which would be negative 2x. So here I have negative 2 root 12. They're the same kind of radical, so I can merge them together. In the denominator, 6 minus 2 is a 4. And negative root 12 plus root 12 cancel each other, which is what's supposed to happen if we used a conjugate. Now notice the 8, the 2, and the 4 all share a common factor of 2. So I can reduce by dividing everything by 2. So this now gives me 4 minus 1 root 12, which I'm just going to write as root 12 instead of having the 1 in front. Dividing by that 4 when I divide by 2 is going to give me 2. Now root 12, although 12 isn't a perfect square, it has a factor that is a perfect square. So I'm now going to write this as 4 minus square root 12 is just like us having square root 4 times square root 3. And I know I'll be able to simplify the square root of 4. And the square root of 4 is just 2. So this gives me 4 minus 2 root 3, dividing everything by 2. And then again, in all three places, we have a common factor of 2. So when I simplify this, and I'm sorry I ran out of space, dividing all three terms by 2 leaves me with 2 minus root 3, all divided by 1, but dividing by 1 just means 2 minus root 3 is our answer. So that is the tangent of 15 degrees. Questions? I know it's a lot of work, but aside from using the formula and knowing your unit circle, all the rest of the work is algebra 2. It's multiplication of fractions and subtraction and addition of fractions and rationalizing the denominator. So that's the algebra 2 part, is the rationalizing denominator. Everything else, though, is just multiplying and adding and subtracting fractions. Okay? So the pre-calculus piece of this really gets taken care of in steps, 1, 2, and 3. So hopefully this isn't so bad as long as you know your formulas. So that's evaluating different things, okay? And I used a bunch of the difference formulas, but if I change this 15 degrees to 75 degrees, well then I could have done 45 plus 30, and then I could have used the sum formulas instead of the difference formulas, okay? So I'm going to move to a different kind of problem, still using these formulas. So in a problem type that asks us to find the cosine of u minus v, where u and v are just two different angles, and I'm telling us that the cosine of u equals negative 15 over 17, such that angle u is between pi and 3 pi over 2, and I'm also telling us that the sine of angle v is 4/5, such that angle v is between 0 and pi over 2. Using the information I have and our cosine difference formula, we should be able to find the answer. So first thing I'm going to do is I'm going to indicate that I'm being asked to find the cosine of angle u minus v. And using the cosine difference formula, if I flip back to a previous page, that would be the cosine of angle u times the cosine of angle v plus the sine of angle u times the sine of angle v. So that's the formula. Of these four terms here that I have, I already know two of them. I know that cosine of u is negative 15 over 17 because that was in the problem itself. I don't yet know the cosine of v though, so that's going to have to stay blank for the time being. Plus, the sine of u I wasn't given either, so that's going to have to stay open. But the sine of angle v I was given in the problem as 4/5, so I'm going to substitute there 4/5. How am I going to find the cosine of v, and how am I going to find the sine of u? Ideas? And we've done something similar before, but where we didn't have two angles, we just had one. So in the past, a problem where we had missing information about the sine of an angle or the cosine of an angle, we made two right triangles, plugged in the information we knew, and used the Pythagorean Theorem formula to find the missing information. So that's what I'm going to do again, but this time I'm going to have two different triangles because I have two angles, u and v. So I'm going to construct one right triangle, and I'm going to use, for this one, angle v. And the information I have about v is that the sine of v is 4/5, which means if v is this angle here in my picture, the opposite is my y, which is 4. The radius is 5. And so the unknown thing is my x. And I can find x using the Pythagorean theorem. X squared plus y squared should equal r squared. So we have x squared plus 4 squared equals 5 squared. So x squared plus 16 equals 25, which means that x squared equals 9, which tells us that x is either positive or negative 9. And remember, this is where you think about the quadrant. Angle V is between 0 and pi over 2 radians, so that's quadrant 1. And in quadrant 1, my x value should be positive. So these two things together now tells me that x has to equal the positive. Oh, sorry, not x, x squared. Sorry, let me do that again. X squared was 9, so x equals positive and negative 3. Someone should have called me out about that. Sorry about that. And so now, since we're in quadrant 1, I know that my x value has to be the positive 3 instead of the negative. And now over here in my formula, I know that the cosine of v should be the x value 3 over the radius value of 5, and it's positive because we know we're in quadrant 1. And then I'm just going to do the same thing, but using angle u and a right triangle with u. So labeling my triangle with angle u. What we knew about u was that the cosine of u was negative 15 over 17. So I knew my x value was negative 15. My radius value was 17. And my y value is unknown. But we can use Pythagorean theorem again. So negative 15 squared plus y squared should give us 17 squared. Negative 15 squared is 225 plus y squared equals 17 squared, which is 289. When I subtract 225 from both sides, I get that y squared equals 64. And then if y squared equals 64, square rooting both sides gives that y equals a positive negative 8. And for angle u, going back to the original wording of the problem, angle u is between pi and 3 pi over 2, which means angle u falls in quadrant 3. Where as far as my y value is concerned, my y value is negative. So now I know that when y equals plus minus 8, in this problem, I really have that y equals negative 8. And so as far as the sine of u is concerned, in my formula, which I didn't know before, I now know that the sine is negative 8 divided by 17. The y value divided by the r value. And now this is just like middle school math. It's just multiplying the fractions together. So multiplying here, negative 15 over 17 times 3/5 would give me a negative 15 times 3 is 45. 17 times 5 is 50 plus 35. So what's that, 85? Plus, now we multiply the other two fractions, but that's going to give us a negative. So I'm just going to have minus. 8 times 4 is 32. 17 times 5 is still 85. And now we just add the two fractions together because we have the same denominator. They're both negative. So we have negative 77 over 85, which is the answer. Questions?
Wait, Mr. Rutledge, I got a question.
Yep.
How you get there? How do you know how to start it off, basically?
So from the beginning, I was told to find the cosine of u minus v. So for that, I know that I'm just using the cosine difference formula, which if I go back, it's right here on the second one. So cosine difference formula multiplies the two cosines and two sines and adds in the middle. So if our angles are u and v, I multiplied the two cosines and sines and added in the middle. Once I had that, of those four terms, I already knew two of them, so I plugged those in blue. And the other ones, I needed to make right triangles for myself to find the missing information. So I labeled the right triangles and then used the Pythagorean theorem to find the missing side, so that for cosine of v and sine of u, I was able to use x over r and y over r using the x value and the y value that I found for both of those triangles.
I got you.
Okay.
I understand.
Other questions there? And again, this is very similar to a problem we've done in the past, but instead of having one angle where I gave you information and you had to find the missing information and think about the quadrant, this time I'm giving you two angles and we had to find the missing things and use the quadrants to find the answer. So it's 1:36. I have one more problem to do. So I am going to go over our half hour. Apologies for that. So last problem is an equation to solve. So we're using our new formulas with solving equations, which we never got to quiz, but hopefully you still remember how to do it. So here, solving cosine of x plus pi over 4 minus cosine of x minus pi over 4 equals 1. I'm not giving us an interval, so we have to solve using the infinite solution set. Notice both of these terms involve a cosine sum and a cosine difference. So for the cosine sum, that first part, I know that's going to be the cosine of x plus the cosine of pi over 4 minus the sine of x times the sine of pi over 4. That part takes care of the first term in the original problem. That's this cosine of x plus pi over 4. For the other piece, cosine of x minus pi over 4, that would be cosine of x times cosine of pi over 4 plus the sine of x times the sine of pi over 4 using the cosine difference formula. In the middle, we have subtraction, and we still equal 1. Now notice, sorry, go ahead, Ari.
Do you have to do all of that, or can you just see that the difference between 1 and 0 to equal 1, it would have to be 1 minus 0?
Well,
so you could just do, the number that works for that is 7 pi over 4.
Well, but there are lots of other numbers that subtract to give a 1 besides just 1 and 0. So I wouldn't take that risk there, assuming that. Before that question, though, there's something critically wrong with what I wrote. And it's because since we're subtracting and the stuff in red is a binomial, 2 terms added, it's hugely important that I had put brackets or another set of parentheses before or after that subtraction, because notice now this subtraction symbol is going to distribute to both of these terms. If you don't put the brackets in there, you're going to mess up the math. If it were addition in the middle, you wouldn't have any problem because a plus symbol distributes to both things to be whatever they were. So when it's addition in the middle of a problem, you wouldn't have a problem. But if it's subtraction, please always remember you would have to put brackets or parentheses so that you don't mess that stuff up. Once I do this now, I have cosine of x, cosine of pi over 4, minus the sine of x, sine of pi over 4, minus, because I'm distributing, cosine of x, cosine pi over 4, minus, because a negative times a positive is still negative, sine of x, sine of pi over 4. All of that is equal to 1. And now I notice that I have cosine of x cosine pi over 4 minus cosine x cosine pi over 4. Those cancel each other. That just gives us 0. For the other two terms, minus sine x sine pi over 4 minus another sine x sine pi over 4, those are also like terms, and they combine to give me negative 2 of those sine x sine pi over 4 terms. Still equals 1. From here, you could either divide by negative 2 on both sides, or you could evaluate the sine of pi over 4 first. That's what I'm going to do. So I have negative 2 times the sine of x times root 2 over 2, because that's my sine of pi over 4. Oops. Still equals 1. Multiplying the numbers together on the left, I have the division of a 2 and the multiplication of a 2, so those 2's just cancel each other out. So dividing by 2 and multiplying by 2 cancels. That leaves me with negative sine of x times root 2, which I'm just going to write with the number in front. So that gives me negative root 2 times the sine of x equals 1 still. I divide both sides by negative root 2 to get sine by itself. So now I have sine of x equals negative 1 over root 2. And because our denominator has a radical, I would multiply top and bottom by that radical 2 to rationalize the denominator. And that gives us sine of x has to equal negative root 2 over 2, which is one of our special angles on the unit, one of our special evaluations on the unit circle. So I feel pretty good about my math. And then remember, at this stage, you could take inverse sine of both sides, or you could just think about your circle. On my circle, I want places where my sine value is negative, so I know I'd be in quadrants 3 and 4. And in order to get root 2 over 2, I'd need our 45-degree angles. So I would need to be in the middle of each of those quadrants. notice here, and let me just indicate, so this angle, if I was on one revolution of the circle from 0 positively, this would be our 5 pi over 4. The one in quadrant 4 would be 7 pi over 4. Here's where I would think to myself, well, from one angle to the next, 5 pi over 4 to 7 pi over 4 is 2 pi over 4, which is just pi over 2. But then from that location all the way back around, I would have a difference of 3 pi over 2, together making up the whole circle of 4 pi over 2, which is 2 pi. Those two things are different, so we have no common difference. So when I go to write my answers, I'm going to have two sets instead of just one. So to finish this, I now know that x equals 5 pi over 4 plus whole integer multiples of full circles to get back to that quadrant, so plus 2k pi, where k lives in the set of integers. That takes care of all of the quadrant 3 answers. I also would have to represent all the quadrant 4 answers, so x also equals 7 pi over 4 plus full circles on top of it or subtracted from it, so plus 2k pi, where k is in the set of integers. So these are my infinite solution sets. Questions there?